Okay, so the second R is going to be repair. On your boards, they sometimes call this not repair, but recovery. So if you see recovery, they're talking about the same thing. We are not talking about DNA repair here. We are talking about DNA repair plus cellular repair. So it's like this recovery of the cell from the radiation injury. So let's start out with the kind of damage that we have. There is, of course, lethal damage. Lethal damage cannot be reversed, cannot be repaired, and leads to cell death. That makes sense. That's the definition of lethal, right? But there are two kinds of damage that are not lethal. One is called sublethal. The second is called potentially lethal. Sublethal is going to be, for us, the most important kind of repair or recovery. Sublethal damage is repaired, any damage that's repaired within hours. And the idea is you give a dose, you wait some time, give a second dose, and that time in between, those hours in between, allow for the damage to be repaired or for the cell to recover. So we call sublethal damage repair SLDR, the increase in survival when a dose is fractionated over time. So this is going to be the second R. The second R is going to be sublethal damage repair or sublethal damage recovery, which is what allows for better survival if we wait time between our fractions than if we don't wait time between our fractions. There is another kind of repair that, in my opinion, is more controversial. It's called potentially lethal damage, and it can be modified by the post-radiation environment. I'll talk about that first to sort of get it out of the way. Here's the idea. The idea is that the dose will be lethal, but somehow modulating the post-irradiation environment actually increases the survival, changes the situation. So what do we here are some examples. You take the cells, you irradiate them, but you incubate them not in this beautiful, wonderful fetal calf serum that has lots of growth factors and nutrients and everything else. Instead, you put them right into a salt solution. They're now sitting in a salt solution. Now they don't accumulate damage as much. They start to repair. Instead of letting the cells grow actively, divide, you take the cells after they've been irradiated and you put them in a density inhibited state where they're growing, where they're very close to each other. They're touching so much that they can't divide. And the third situation is any conditions that are suboptimal for growth. The relevance to therapy has been questioned here. I need to say point blank that I don't believe in this. I actually believe this is a cell cycle effect. And what you're doing is you're putting the cells in G0, which is, as we just learned, the most radio-resistant period that the cell can be in. But that's not what you answer on your boards. You answer exactly this, that it's a dose that would be lethal, but modulation of the post-radiation conditions allows for an increase in survival. Here's the example. Log the surviving fraction against dose. This is where you treat the cells immediately. Here's the survival curve. Now, instead, you density arrest the cells, you take them out and you put them so they're touching each other for 6 to 12 hours, and you see this change in survival. This is called, this difference between the two of these is PLDR, potentially lethal damage repair or potentially lethal damage recovery. Here's another example where they wait hours before plating the cells and they show the same kind of effect. And then the question becomes, does this work in vivo? And Jack Little, who passed away at Harvard this maybe 6 months ago, I'm actually speaking in his memorial symposium in a month. Jack demonstrated that it does occur in vivo by looking at a solid tumor which has no density inhibition and a large tumor where there's a density inhibited state, and showing that in fact you can get increased repair here. So these are the classic studies that suggest that potentially lethal damage repair is important. And one other point is that there is no PLDR following high LET radiation. And in fact, there's going to be no sublethal damage repair following high LET either, or it's going to be very little. I mean, I can argue with this point. I actually have data that argue it, but for our purposes and for the board's purposes, you say there's no repair following high LET exposures. It's a major difference between high and low LET radiations. Okay, so now let's go to the most important repair, the sublethal damage repair, SLDR, as we usually call it. It's defined as the increase in survival when a dose is split into 2 or more fractions that are separated by some unit of time. There will be a point at which you can increase the number of fractions and you will not increase survival. So there is a plateau in the response. Let's look at that first. Here is log the surviving fraction against dose, but this dose is expressed in fractions. Here's the single dose and the split dose right here. It's change in the survival when you give a different dose rate. Now you give a dose rate out here, 8 fractions, 20 fractions, 30 fractions. Do you see a difference between 20 and 30 fractions? Not much. That means that there's a point at which you can now separate dose and repair is not significantly affected. So it's kind of like the repair maxes itself out. And that is around 20 to 30 fractions. And that's why, you know, going up to 50 fractions in a patient, while it would also be very painful to administer, it has no value at all. So what is the best time for time interval between fractions? This is frequently a board's question. This is the in vitro experiment, and then we'll look at the in vivo experiment later. So in vitro, here's what they did. They took Chinese hamster ovary cells. They gave them a dose of 7.6 gray, followed immediately by 7.95 gray. And here's what they got right here. Now they gave 7.6, waited an hour, and gave 7.9. They waited 2 hours between the two. They waited 3 hours, 5 hours, et cetera, et cetera. What does this show? This shows that let it go for 2 hours and you're getting improved repair. But after 2 hours, there's no difference. So what that would argue is that you need to wait at least 2 hours between your fractions. This is an in vitro situation. The in vivo data we'll look at in a minute, but most people, and on your board, say that most repair occurs between 4 and 6 hours in vivo. So that means we would never want to give a fraction that is not separated by 4 to 6 hours. And most people would say 6 hours is probably the best, the safest. So you wouldn't want to give a fraction and then an hour later give another fraction. You'd want to wait 6 hours to maximize the repair. So here we go. Let's look at the 2 R's that we've learned so far. The first R is this reassortment in the cell cycle, where as the cells are going through the cell cycle, they become enter into a more resistant phase with the radiation. This is going to occur in the first 6 to 10 hours after. What's happening during the first 2 hours in vitro, 4 to 6 hours in vivo, that's repair. So think about it from this perspective. You give a dose of radiation, you wait some time, give the second dose of radiation, and what are we allowing to repair? We're allowing the normal tissue to repair. So the purpose of fractionation in this example for repair is to spare normal tissue. Are we sparing the tumor? We are, and that's the problem, but it's more important to spare the normal tissue. It gives us a better advantage. So why do we fractionate? Number one, because it allows us to reassort the different sensitive phases of the cell cycle, and number two, because it allows for normal tissue to repair. Now, I'm going to bring up the third R because there's not really a chapter that deals with it right now. What's the problem that goes on when you're fractionating? As you fractionate, you're giving the tumor more time to repopulate. So if you could kill all the tumor in one dose, you would have no repopulation. But as you fractionate, spread out your treatment time, you're allowing the tumor to repopulate. So that's the third R, radiobiology. Those are the 3 things we need to consider. The fourth one that we'll talk about next is going to be reoxygenation. Okay. There will be, when we get to the point of talking about treatment regimens and fractionation regimens, there will be treatment regimens that are going to be dependent upon how fast is the tumor growing? What is the potential doubling time of the tumor? And we will choose different fractionation patterns based on that. Here are the in vivo data. In this example, they used a mouse create a tumor which grows as an acidic fluid in the tumor. Looked at its repair time. This is the repair time of the tumor. This is the repair time of the normal tissue. What is this showing? 6 hours, 8 hours. Here is 6 hours, 8 hours again. So the tumor is repairing, the normal tissue is repairing. We wish the tumor wasn't repairing. We can't help it, but we do want to spare the normal tissue, and therefore we're glad it repairs. Okay, so we said this already, log the strength fraction against dose. Here's the single dose, here's the split dose. If we looked at this over time, what would we see? We would see that repair is happening in all tissues, regardless of whether they're cycling or not, during the first 2 to 4, 6 hours. When do the cells reassort in the cell cycle? Only if they're cycling, we would see this dip because of reassortment. We don't see it if the cells are not cycling. Of course, that you can't get reassortment in the cell cycle if the cells aren't cycling. And then finally, the tumor itself is going to continue to proliferate. And in fact, there will be some normal tissues that will proliferate as well, and we'll talk about those as time progresses. So we already said that for high LAT radiations like neutrons, there is no repair, there's no potential lethal damage repair. Here are the data, recovery factor or the repair factor against time after splitting the dose. Here's the split dose of 4 and 4 gray for X-rays. Here's the split dose of 1.4 plus 1.4 gray for neutrons, waiting 1 hour, 2 hours, 3 hours between each dose. What you notice is there's significant repair here happening with the X-rays, not much repair happening with the neutrons. I can argue that and tell you that at very low dose rates, there's some repair, but at the clinically relevant dose rates for neutrons, there's no repair. And that's how you answer it on your boards. So what happens, we've seen this before, log the surviving fraction against dose, give a single dose, now give a fractionated dose. What do? We effectively pull out this survival curve and allow for improved survival of the cells when they're fractionating. And not only is it improved survival, there's a decrease in chromosome abnormalities. Of course, there's a decrease in dicentrics and rings, the ones that are associated with lethality, but even with other ones that are not associated with lethality, they're also decreased because of this. Okay, all this is about fractionation, but now we're going to move into low dose rate. When do we see low dose rate in our clinical practice? We see it during brachytherapy. When do we see low dose rate in our exposures? We see them in our occupational exposures and those of our people that work with us. So understanding low dose rate is very important for the boards. Here is log the surviving fraction versus dose. And this is for cells that have been given 3 different dose rates of exposure. And what you should see immediately is 1 and 7 gray per minute have almost no difference. Go up to 5 milligray per minute, and now you get a significant improvement in survival. Why do you have an improvement in survival with low dose rate? It's because probably we're allowing for repair to take place because we're giving the radiation dose while it's continuous, it's at a very low level. This number is very important to know. The dose rate effect is most evident between 0.01 and 1 gray per minute. Go over 1 gray per minute like this, 1 versus 7 gray per minute, no difference. Go under 0.01 gray per minute and you don't see a significant difference either. So this is the range, and that is asked on the boards frequently. It's asked in ways like, you are giving cells 0.02, 0.05, 1 and 8 gray per minute. Which ones do you expect to show a dose rate effect? And you know there's going to be no difference between the 1 and the 8 gray per minute, but there will be for the others. So that's frequently asked on the boards. Does this occur in vivo? And the answer is, here are the CHO cells. These cells were the HeLa cells. Let's go to the CHO cells. Log the surviving fraction against dose again. Here is 1 gray per minute, 0.3 gray per minute, 160 gray per minute. Look at this up here, 3.6 gray milligrade per minute. What's going on here? Let's just look at 15 gray dose. 15 gray dose in the Chinese hamster ovary cells gives us a survival fraction that's very low. The same dose given at a very low dose rate gives us almost no decrement in cell survival. So dose rate is everything here. Again, as long as it's within those magic dose rates, it's fine. This was a study done comparing 40 different cell lines for a high dose rate versus a low dose rate exposure. Now, you should notice that some cells don't show a difference between low and high dose rate. It's rare, but there's some that don't show any difference at all. But if there is any difference at all, it's a trend toward improved survival at the low dose rate compared to the high dose rate. And this just shows the same example. With a decreasing dose rate, you get improved survival. So it's just something. Does this happen in vivo? The answer is yes, it does. Here are the jejunal crypt cells that were done for very rapidly dividing cells. Here is the high dose rate, the low dose rate. Look at this difference in survival, very dramatic. So this occurs not just in vitro, but in vivo. But there is an exception. And the exception is called the inverse dose rate effect. 4 years ago, I would have told you, don't even bother with this, it's not on the boards. But then they put it on the boards. What is an inverse dose rate effect? It's shown here for a particular type of HeLa cells called HeLa S cells. These cells have worse killing at low dose rates than they have at high dose rates. I'm sorry, my phone just. Worse killing at high dose rates than they have worse killing at low dose rates than they have at high dose rates. This was called the inverse dose rate effect, and you need to know that that's what it means. They asked the definition on the boards, and that's all. Okay, so what's the mechanism? I don't think you need another mechanism, but the idea is that the cells have a G2 block. There is this that if the G2 block occurs, as the cells are progressing through the cell cycle, they come up into G2. G2 is the most radio-resistant phase of the cell cycle, and so there we go. And this just shows the sort of pattern of repair, which is occurring with the low dose rates, proliferation being effective at lower dose rates, et cetera, kind of pointing out exactly what we just said, where an acute high dose rate versus a low dose rate causes this difference in survival. We're not going to talk about this example because it's not relevant at this point in time. But time frame. Here is the time frame for repopulation, which is going to be the period of time of a cell cycle. Reassortment in the cell cycle is going to be even longer. Recovery takes even longer, and then reoxygenation is going to take time and less time. And those are things we're going to have to think about as we progress through this. Here's log of the surviving fraction against radiation dose, comparing survival for 4 different cell lines that have been irradiated at high dose rates and at low dose rate, at high dose rates and low dose rates here. And you can see this difference in survival. Okay. Now there are going to be exceptions to the rule. I mentioned those HeLa cells which have an inverse dose rate effect. There are a few cells in the body that are going to be more sensitive at low dose rates. One is measured right here, and this is mentioned for rats. But here are I'm going to try to put it in perspective. So there were a large number of animal studies that were done at Argonne National Laboratory in the 1980s and 1990s. And what they did is they looked at different dose rates and how they impacted survival. So here is a high dose rate exposure with the beagle dog, with the mouse, and I will tell you, these are like data sets with like 49,000 mice and 30,000 dogs. Given a low dose rate, given a very high dose rate per day. Here are same animal colonies, but this time they were given a very low dose rate per day. Way big difference. Think about it for yourself. If you got all of your occupational exposure and environmental exposure in one day, you would drop over dead from the radiation. But because you get it over your entire lifetime, it does not have so dramatic an effect. So there is this dose rate effect that works on us at the whole organism level. But there are a few cells where the stem cells are extremely sensitive, they have a long cell cycle time, and there are differences in the tissues to adapt. And because of that, we can put together these 3 R's and say that this issue of repair is going to make a very big difference because the cells are partially synchronized. I'm going to skip this. This is the key point I want to make. And this is a board's question, almost in exact words. So at very low dose rates, in general, what we expect to happen is you're going to have better survival of the organism and of cells in culture. You're going to have fewer mutations. We didn't look at mutation data, but you'll have fewer mutations. We did look at chromosomal aberrations and said there are fewer chromosomal aberrations at low dose rates compared to the same dose given at a high dose rate. We just saw the lifespan data from animals and extrapolated to human and said it's the same thing for human. But there are 2 exceptions to this that you need to know for your boards. Exception number 1 is going to be the testis. The testis is the one dose rate sensitive organ in the body. It is more sensitive to low dose rates than high dose rates, and it has to do with the cell cycle turnover of the spermatogonia in the testis. The second example, and we're going to talk about both of these when the time comes. We'll talk about the testis when the testis comes up, and we'll talk about the second example. The second example is the fetus. When the fetus is exposed in utero, if all of the dose is given in one pop, it's better than if that same dose is spread out throughout the duration of the pregnancy. Why? Because you're more likely to affect many phases of gestation if you give it throughout the duration of the pregnancy. But if you give it in one go, you're less likely to hit a sensitive phase of gestation. So those are the 2 exceptions, the testis and fetus, and everything else is pretty much with, while there are some differences from one cancer cell line to another, for most normal cells, as you have a low dose rate, you improve survival compared to the same dose given at a high dose rate. So now let's move this into brachytherapy. So brachy comes from Greek word meaning short range. We generally give 2 kinds of brachytherapy, although we'll mention a few others that people are talking about. One is intracavity, where we take a radioactive source, we stick it in a body cavity, normally the uterine cervix. It's in close proximity to the tumor. The second is interstitial brachytherapy, where we take radioactive seeds and implant them into the tumor volume. Okay, so intracavity brachytherapy is usually we implant this. It's a source. It's temporary. It goes in for a few days. The dose rate is 5 centigrade per hour, for instance. Uterine cervix is the prime example I know. We used to use radium and cesium. Now we tend to use iridium, which has gives lower energy, but it has a shorter half-life. Why do we use this in the uterine cervix? Because the high dose rate complications from an external beam exposure of 3 to 12 dose fractions will affect the rectum and the bladder, which is going to affect lifestyle. So by giving a lower dose rate, what are we doing? We're preserving the normal tissues around it, but still getting the dose to the tumor. Exactly the same thing with interstitial brachytherapy. Again, usually using iridium these days, normally using it for prostate as the most common, where 100 or so reactive seeds are implanted in the prostate. Again, it's the same idea. You're trying to minimize toxicity to the bladder and the rectum. And it's at a case where giving a 60 grade dose, for 7 days is going to be significantly damaging. There are a few examples of permanent interstitial implants that are used. These tend to be used in examples where you don't want to do a second surgery to remove it. So what is done in these examples is we put the source in. It has a generally short half-life, but it's got an initially pretty high load-up rate. So I-125 is really common for this. So the total dose is really high initially, but in 60 days it decreases. That's the length of its first half-life. And again, it's going to be very useful in certain kinds of tumors. The difference between the brachytherapy and the external beam is that with brachytherapy, we're going to get really great killing close to the source. But as you move further from the source, we're not going to. We won't see this so much with external beam, but because we can keep giving more and more external beam, we can now get better killing in that area. We also need to know that there is only a certain distance that these photons can travel. They have different kinds of energies. Iridium has become the common I-125 in some examples, but there's a lot of work now going into americium, ytterbium, a large number of other radionuclides that might be of value here. It needs to be mentioned that there are two things. First of all, the distance that the photon can travel depends upon the kind of energy. Please notice beta particles almost always travel further than alpha particles. These distances for the I-125 and bromium are not good because they're only giving you the distances of the Auger electrons, which are not the prime damaging agents there. You need to look a little further there. But the problem is that can we get enough energy deposited in the tumor to kill it? If it's a small tumor, we probably stand a good chance. If it's a big tumor, we probably can't get enough energy in. And that's why we have to go and use external beam for a lot of these larger tumors, because there's just not an approach that can give us enough energy to kill a smaller one. And this is a blown up portion of that early top part showing the distances of tumor diameter that you can get killing and the number of cells that are killed. I will mention that interventional radiologists often now are using these like Y90 microspheres because of their large number of cells that they can get killed and because of the pretty good distance that they can get damaging agents. And this just shows the same thing but from a different perspective. For external beam, we can combine multiple beams to get us bigger killing of a larger number of cells, whereas with a radioisotope, there's going to be an optimal size, and beyond that, we're not going to be able to do much no matter what we do. We're going to talk about early versus late responding tissues much later in here, and I don't think it's going to help us to talk about it now. But I will bring up that there are a lot of data that have been done in comparing local control and dose rate effects. And clearly, the increased necrosis is seen with higher dose rate, and oftentimes the high dose rate doesn't have that much of a difference in local control. Here's a correlation of dose rate with recurrence. I'm not sure that this is statistically significant, but it was an early study using iridium 192, and you can see that from here to here it's probably significant. I'm not sure from here to here or here to here that it is. So it just varies. Now, an old method that has become brought up to the fore again more recently is the use of radiolabeled antibodies. In the early days, they went after things like ferritin. Ferritin is expressed at very high levels in many tumors. What they did is they used, in Hodgkin's disease, they made a monoclonal antibody. They actually just made antibodies against ferritin, radiolabeled them, and sent them in to fight Hodgkin's disease. And they had some success, but it wasn't as much as they wanted. They first made monoclonal antibodies, and now they're making these chimeric antibodies that have a humanized component to them, and they add these to the tumor. And this should be a Y90, not YT90. This is yttrium, and they use this to treat, and they've had some pretty good results, particularly combined with chemotherapy. Here are just some older data where they've targeted a variety of different markers, but I will tell you this field is still very much alive today. I just reviewed a proposal the other day that's using a PMSA target with radiolabel to try to go after it. And they're just doing it with larger constructs that are nano constructs, for instance, and other similar approaches. And here are just some other studies that have been done, again, showing really a pretty good clinical significance for treatment with these. We'll talk about SPECT later. And so here's the summary. So there's sublethal damage repair that we have talked about that allows for, or sublethal damage recovery that is important in the tumor response to radiation. Potentially lethal damage repair or recovery is also there, but it's not as important for us clinically. We learned about 3 of the 4 R's here. We learned about reassortment in the cell cycle in the previous lecture. We learned about redistribution and repair here. Actually, this should be repopulation. That's a typo. Redistribution and reassortment are actually the same thing, redistribution in the cell cycle. There's a dose rate effect on cell survival. These are observed in most cell lines. And brachytherapy takes advantage of that local control